Okay, so this, you'll definitely see a problem very similar to this example on the quiz next week. Okay, so alert, star this in your notes. Okay, except it won't be flip a coin 40 times, or this one was Los Angeles County is 41% Latino, and this. Okay, it's gonna be something else, right?
You change the figures.
I'm gonna change the figure. I'm gonna change the example, right? It's going to be the percentage of something is this. If you take a sample of this, what's the probability you get this percentage or more, or this percentage or less, okay? It's going to be similar to this. You can make up your own examples and try it out yourself, okay? That's what I always say. Try making up a problem for yourself. All right, so there is I guess a few warnings or things that we have to take into consideration. Okay, we use the normal distribution here. Okay, but the truth is that the normal distribution doesn't always work, right? Because we said when you take a bunch of samples and you look at the different p-hats and you make a histogram of all the p-hats, you got a normal distribution. Okay? But the truth is, sometimes you make a histogram of all the p-hats and it doesn't look like the normal distribution. And if it doesn't look like the normal distribution, this thing doesn't work. So there's a few conditions that we have to meet in order to make sure that the normal distribution works, or what we call in order to make sure that the central limit theorem applies. Okay, so conditions to make sure the central limit theorem applies.
Which is a normal distribution, right?
Yeah, so central limit theorem applies, or in other words, conditions to make sure we can use the normal distribution.
So central limit theorems mean normal distribution. Okay?
Does anyone have a Panadol?
What do you need?
Panadol.
A pen?
Panadol. For a headache.
Tylenol.
Does anyone have? Oh, fabulous.
Acetaminophen. Do not exceed more than 4,000 milligrams per day. 2,000.
It's facts and figures.
What do you call it?
Acetaminophen? Or,
Oh, I called it acetaminophen.
acetaminophen? I don't know.
Oh, I didn't know if that was like on
It's her
the
brother.
It is on.
Two?
But you can walk across. No worries.
They're extra strength.
Yeah.
Oh, good.
Two is
I want to
more
go for
than-
that.
Okay. All right. What is the central limit theorem? The central limit theorem is the idea that a sampling distribution looks like the normal distribution. Okay? But it doesn't always. Okay? So we have to make sure these conditions are met. Number one condition.
Wait, so the central limit theorem is also the normal distribution?
It's not.
Oh.
It's the central limit theorem is not the normal distribution. Otherwise, I'd just say it's the normal distribution. The central limit theorem is the idea that you can use the normal distribution.
Oh.
Okay. All right. It's like I don't know. It's the idea that you can use the normal distribution for a sampling distribution. And what's a sampling distribution? It's the distribution of all possible p-hats ever from all the samples that we're taking. Okay. It's a weird concept. All right, so the first one is that our sample needs to be selected randomly, okay, or and independently. So that, what that means is that you can't go and ask your friends to be the survey or the sample. Okay? Right, if I were to, if I want to know what percentage of LA is Latino, and I were to ask all of my friends, my proportion that I get from that estimate is going to be different from if someone else asked, you know, their things, or if they did a true random survey and things like that. Okay? Because you know, as much as, you know, I'd like to think I have a diverse group of friends, it's not going to be truly reflective of Los Angeles County. Okay? So the sample needs to be selected randomly and independent of one another. Okay? Otherwise, it won't be representative of the population. Okay? And then there's two things. The sample needs to be, can't be too small, and the population, and the sample can't be too big. Okay? So we've got, the sample can't be too small and the sample can't be too big. We give these two things a few different names. Okay? So sample not too big. Okay? Or compared to the population. Okay, and this condition is called the big population condition. Okay, meaning the population has to be at least 10 times bigger than the sample. And the reason why this is important is because if your sample gets too big, it starts changing what's left in the population. Okay? So, you know, if you think about a deck of cards, you got 52 cards, 26 are red, 26 are black, right? You pick one out, you got a 50-50 chance of it being red or black. However, after you've taken 10 cards out of the deck, it's no longer necessarily going to be 50% red, 50% black, okay? Because you've changed, like if I've taken 10 cards and 8 of them are red and 2 are black, then what's left in the deck is a different proportion. So what we're hoping is that the population is so big that anytime you select things out of the deck, it doesn't mess up what's left in the population. So the population needs to be at least 10 times bigger than the sample. So if you're taking a sample of 100, how big does your population have to be?
1,000 or more.
At least 1,000 or more. At least 1,000 or more. Okay. 10 times bigger than the sample. Okay. And the sample can't be too small. Okay. And this is the large sample condition. This first one is the independent random condition, or random independent condition. Alright, so the large sample condition, this one's a little bit more weird to check. Okay, a little more complicated to check. And to check this one, there's two things you have to check. N times P has to be bigger than or equal to 10, and N times 1 minus P has to be bigger than or equal to 10. Okay. And if P is not given, use P hat. Okay, so if N is, or I'm sorry, if P, if we're doing a coin flips, okay, P is 0.5, right? What's the smallest number of, fewest number of coin flips that I can have in my sample? What's the smallest n that I can use?
1.
No? If P is 0.5, what's the smallest n that I can use? $20. 20 would be the smallest that I can use. Because 20 times 0.5 is 10, so that would qualify. And 20 times 1 minus 0.5, which is also 0.5, 20 times 0.5 is also bigger than 10. Okay, so that checks out. If I use n is equal to 18, then these conditions aren't met, because 18 times 0.5 gives me 9, and 18 times 1 minus 0.5 gives me 9. Both of these numbers have to be bigger than 10. Okay. So let's, let me just write an example out. Okay, so let's say you go, you decide to conduct a survey. Okay. So you go, you post a survey on Reddit, okay, and ask Reddit.com, it's a website, what percent is, I don't know, is some trait, okay.
Funny.
No. Funny is such a subjective thing. Okay. Okay. Well, what percent is would consider themselves liberal? Okay. And you get responses from 400. And your p hat is 62%. Okay. And then we'll say, all right.
You can use p hat instead of p.
Huh? Yeah. Okay. So, are any of these conditions violated?
You're basing it on those two, right? If they're violated.
Are any of the conditions violated? So this is a scenario, right? You want to know, do an internet survey.
Me too. Continue that.
So there's 3 conditions we have to check. Are any of them violated?
It is random.
Yes, the first one.
The first one is violated.
Yep.
Is this an independent,
Yes.
random and independent survey?
Yes. Or it's only people on Reddit.
Yeah, only people on Reddit, okay?
Right.
So this is not a random sample, okay? Even if you were just trying to figure out what percentage of Reddit is liberal, okay? This is still not a random sample. Why?
Because of the bias, because of the people that wanted to.
Only people who want to respond to this survey are gonna respond. Only you got voluntary response here also. Okay, so this is not a random survey. Okay, so central limit theorem does not work. Is that okay with everyone?
Just because it was on one website,
Because it's on a website and it's it's an internet survey. Okay, pretty much all internet surveys will not be random. There's no way to do a random internet survey. Why?
Because it's volunteer. It's
Well,
volunteer response.
voluntary
It's
response.
one. You're choosing to go to
And
the website.
Internet users is not representative of the world or population or
Yeah.
anything, right? Like you're not gonna get anybody who doesn't have the internet, and there's a bunch of people who don't have the internet. Okay, yeah.
So the central limit theorem only applies to things for everywhere in the world?
No.
Well, then how come if you were to change the internet to Los Angeles, like what percent is liberal? So that wouldn't be.
Okay, well, okay, so it depends on what is the parameter we're trying to get here, okay? So first we have to decide what our parameter is, okay? So our parameter here, okay, if it's what percent of the internet is liberal, well that's certainly not gonna work because we have only posted the question on Reddit.
Well, what percent of
If we ask what
Reddit.com
percentage of Reddit is liberal, okay, then it's still not going to be random because of voluntary response. Only people who choose to respond to the survey.
What if you somehow made it that they had to?
Yeah, okay, so now if you forced people and they say, oh, we've locked out the website until you respond to this survey, and so that everybody is forced to, then maybe you can get
so
either a
all
random.
voluntary responses are not in
Yeah,
the
and anytime you've got voluntary response, you're gonna violate this thing, okay? So it's truly, well, okay. It's really hard to pull off a truly random survey, okay?
Thank you.
Huh?
But even
Oh.
stopping people at the street is right. It's like.
Yeah, stopping people on the street
Voluntary.
is not gonna be a response. Well,
It is
first off,
voluntary.
when you get people on the street, it's not even random. It's not even random, okay? Because not everybody walks on the street. So if you go around Los Angeles and you're asking people on the street, you're gonna miss people who are afraid of walking on the street, okay? I mean, it sounds silly, but there are people who won't be seen walking down the street, okay? And so you're not gonna be able to survey those people. And huh?
No, someone said me. I'm like.
And so if you do a survey on the street, it's not gonna work, right? And certainly you're not gonna get anybody who doesn't walk down that particular street either. Okay?
Can you give us an example of one that is?
A random survey?
Yeah.
Yeah, it's really hard to do. Truly random surveys today are conducted usually by telephone, and they're about 99% of the United States can be reached by telephone. So they're willing to sacrifice that 1% that they're gonna miss, and they do random digit dialing. Okay, a computer just generates a random number and dials it. They don't go with a phone book. They don't go with anything like that. The computer just generates a number, it dials, and then they get an answer, and so there's still some non-response bias, but a lot of research has been done to try to counteract that. Yes.
But again, that's voluntary. I mean, when I
Yeah,
get
you
someone
know,
who
I
calls
know.
and asks me questions, I normally hang up and
That's
say,
very, very
"Don't
true.
call
That's
again."
very true. So a true random sample is almost impossible to pull off. Okay.
Like from surveys, you can do that.
It's yeah. So a lot of times on these things, I'm just gonna say you randomly select.
Right.
All right. And then so if you see the words you randomly select something, then the random and independent condition is
It's been met, yeah.
Okay. All right. But this phrase here, it's like truly, it's like $1 million has gone into random selection here. Okay.
So I have one other question.
Yeah.
If you then take like, I don't know, all of your students in this classroom and say, the ones I pick, if you don't answer these questions, I'm not like you make them, like if you wanna get your grade, you have to.
Yeah, sure.
That would be, if you're trying to do something for just our classroom, that would be.
Yeah, okay, so that would work, okay. But if I survey everyone in the class, then I've violated the big population, right? Because then I'm no longer dealing with a sample that's 1/10 of my class. But you're right, I could do something, like if I want to survey and then I forced you guys
Or if
somehow.
UCLA wanted to survey, they had
Right.
each class take a certain
Yeah,
amount
yeah,
of
that
questions.
could work, that could work. So, you can do random surveys, at like institutions where you know everybody and things like that, but but for the country, very challenging. Okay.
I have a question.
Yes.
So, if we were to check
say you randomly select 80 people from.
So then we stop there. We don't answer the question, right? We just
Yeah,
stop
we don't.
there.
We don't.
We don't even proceed.
There isn't even a question here. Okay.
Yeah, you just said to.
I just asked.
All
you,
right,
are
that's
they
true.
equal
That's okay.
conditions
Yeah, what is?
violated?
Yeah, you did. What percent is liberal? You did answer.
Yeah, and my response, my sample statistic is 62%. Okay, so I randomly select 80 people from UCLA, and we want to, we want to know the proportion of UCLA students I don't know, with tattoos. Okay. And we'll say 10%, I don't know. It's probably higher than that. Okay, so we'll say p hat equals 10% at tattoos. Are any conditions violated? So the three I need to check.
P-hat is too small.
So the big population is 80. Like the full population is 80 people, or is it UCLA students?
80 people is my sample. Alright, so in this one, the large sample condition is violated, okay? So what is my n? My n is 80, and I don't have p, but I've got p hat. P hat is 10%, so 0.1. So if I check large sample, I get n times p is equal to 8, and n times 1 minus p is 72. Okay, so 72 is bigger than 10, but 8 is not bigger than 10. So the large sample condition is violated, okay? Random and independent is met because I said I randomly select, alright, however we did that. Okay, and then what about big population? I did not tell you the population size, okay? But how big does the population need to be for me to use a sample size of 80?
10 times.
It's got to be at least 10 times 80, so population must be at least 800. Alright, so are there more than 800 students at UCLA? Yes, so that's met.
So you've just ticked all of the conditions right now, basically.
Yeah, so I have to check them all. I have to check all three, okay?
Right.
And this one for the large sample was not met.
The large sample, which
Because
one is that one? That one, right?
N
The 8?
times p and n times 1 minus p
N
have
times
to both be bigger than 10.
P. N
And-
times P?
Yeah, n times p. What is n times p? 80 times 0.1
Right.
is 8.
So that is smaller than 10.
Smaller than 10, so that condition is violated.
Right, because it has to be bigger than 10.
Yes. Both n times 1 and n minus p and n times p has to be bigger than 10. Both of those have to be bigger than 10.
Oh, so because that one is not bigger than 10, then it's bad.
Yeah, because that one's not bigger than 10, it's bad, and the whole thing breaks.
Okay,
And
and then
then-
the population must be at least 800.
Population, so the big population must be at least 10 times bigger than the
Okay,
sample.
fine, got it.
My sample is 80, 80 times 10 is 800.
Got it.
So is the population at least 800? In this case, proportion of UCLA students with tattoos, or I mean, all of UCLA students.
Which condition, sorry, which condition is the one for N brackets 1 minus P?
That's the same. So large sample condition has two things
Two
you have to check.
areas.
There's
Okay,
two
okay.
things. Okay.
So for the first one it says no and the second one says yes.
Yeah,
Because you're
so they
taking-
both have to be bigger than 10. This
So-
one's bigger than 10, but this one's not, so
Everything's out.
it's out.
Okay.
Yeah. These are, it's an all or
Nothing.
fail, yeah. All of the conditions are met, or it doesn't work. Okay, so you'll have a few questions like this on the quiz next week where I describe a scenario and I say, are the conditions met or not? And if not, which one is violated? Okay. Alright, so last part.
Sorry, one more time. The big population, sorry.
That's okay.
I'm still a little lost on that.
No, just, I understood that part, it's great. But the big population must be 10 times bigger than what? 10 times bigger than?
The sample.
The sample, okay, that's fine.
Okay, so what is my sample?
80.
How big's my sample? My sample is 80, because I
Right.
selected 80 people.
Right.
So what is 10 times 80? 800.
800.
So my population has to be at least
10 times bigger than the sample.
10 times bigger than 80. So it has to be at least 800. So what is the population in this case? All UCLA students. Is there more than 800 students at UCLA? Or are there? Yes, well, there are.
So, but that doesn't work because 8 is not bigger than 10,
No,
right?
it does work.
Because you said it's all or nothing.
Right. Okay. So we have to check 3 conditions, right? So we checked the random independent condition. Is that met? Yes, because I said randomly select. Big population, is that met? Yes, because the population is over 800. Large sample condition, is that met? No, because n times p is not bigger than 10. So because of that, this fails. We cannot use the normal distribution. And that's just how it goes. Alright. So with the normal distribution or the central limit theorem, we were able to say, answer questions like, if I flip a coin 40 times, what's the probability of getting 60% heads or more? Okay, right? We're okay with that question, I hope. Okay, now we're going to do the opposite. Now I have no idea what the population looks like. Okay, so another one was that we said in the population 41% are Latino. If I select 200 people, what's the probability that 38% or fewer of my sample is Latino? Okay. Now we're going to switch it up. Okay, let's say we wanted to know what percentage of Los Angeles was Asian. Okay, so maybe we surveyed 100 people, and we said, "Are you Asian or do you identify as Asian?" And a certain percentage responded. Okay. Now we want to say, based on the results of this sample, what can we say about the population? So let's say I surveyed 200 people in Los Angeles, and 23% of my sample said they were Asian or identified as Asian. Okay, so 23%. What proportion? What's my population parameter? The proportion in the population that's Asian. Do we know that number? No, we don't. Okay, we don't know that number. But what we're going to do is we're going to say, okay, well, my sample had 23% Asian. Okay, 23% of my sample was Asian. So, what does that tell us about the population?
Is this like how we went back to the table and then we looked for the percent in the center and then we took out you know what I'm referring to?
I don't.
You know how some of the problems, we went and looked at the actual z-score?
Okay.
And the other
no,
ones
no,
we
no,
did
no,
the
no. Okay,
percent.
this is not that.
Okay.
Okay. All right. So so once again, I surveyed 200 people. 23% of the people I surveyed said they were Asian. Okay. So if somebody said, what percentage of Los Angeles is Asian, what would you tell that person? Okay, you'd say, I don't know exactly what percentage of Los Angeles is Asian, okay? But I did take a survey, and 23% out of 200 were Asian. So based on that survey, I'm going to estimate that Los Angeles is something around between 20 and 25% Asian or something like that. Does that make sense? Okay? Because you observed a sample, But you don't know if this number 23% is higher than the true value or lower than the true value. Okay? But we do know it should be somewhat close to it. It shouldn't be too far away, right? And so because it shouldn't be too far away, we can say, you know, I'm pretty confident that the proportion in Los Angeles that's Asian is going to be between these two numbers, or within some range here. Okay, so I'm pretty confident that Los Angeles is not going to be 90% Asian, and I'm also pretty confident that it's not going to be 1% or 0% Asian. Okay, because my sample revealed 22% or 23%, whatever number it is. Okay, does that make sense? So this idea here is we are creating a confidence interval, okay? So the idea is we observe a sample sample has proportion p hat with a certain trait or characteristic. Based on this sample, we're creating a range of plausible values of P, the population parameter. Plausible values.
What is that?
Like
When something's possible, like the probability of
It's
it
like
being happening.
possible, but
Possible.
it's not possible.
It's more.
It's more like
credibility.
Probable.
something that we can
foresee.
conceive, okay, in our
Yeah.
mind. Okay, conceive is not the right word.
Like
Something that we
there's
can
a-
imagine it to be
possible.
or believe it to be.
Yeah.
Okay, because if I use the word possible to say if it would be impossible to be outside of that range. Okay,
Right.
and it's not that it's impossible. It's just
Likely.
The
we
credibility
don't
of something.
believe it. We don't believe it. Yeah, it's not. It's a little incredible to us.
Correct.
Okay. So plausible. Okay. So let's say I take a sample and 22% was Asian. Okay. What are plausible values for the true proportion that are Asian in LA County? Something around 20%. Maybe between, or I'm sorry, something around 22%. So maybe between 20% and 24% or something like that. Is it possible that the true proportion in Los Angeles County is 15%?
Yeah.
It is
Can be
possible.
lower, yeah.
It's possible.
Maybe not plausible.
Okay, yeah, maybe not plausible, but it's possible. If the true proportion in LA County that's Asian is actually 15%, what does it mean for me to have gotten a sample that was 22% Asian? Maybe not that I did something wrong, but because of the nature of randomness, I happened to get a more Asians in my sample, just because of randomness, right? Like if you flip a coin 100 times, it's possible to get 70% heads. Okay, unlikely, but it's possible. Okay, and in the same way, if the true proportion is 15%, it's still possible to get 22%. But what we're saying is that based on the sample of 22%, the plausible range is between 20 and 24%. But yes, it's still possible that the parameter, the portion in the population is something different. Okay? So how do we create this range of plausible values? Well, what should go in the middle of this plausible range? 22. My p hat, whatever I observed in my sample, that should go right in the middle, right?
Did you say it was 23?
I don't remember what I said. Maybe I said 23. Okay, I'm just making up numbers, right? So, okay, so whatever I said my p hat was, whatever proportion that I observed, this goes in the middle. So the observed proportion okay, and this is what they do during election season. They say so and so is polling at this thing with a margin of error of this percent, right? They'll say so and so is polling 48% of the votes with a margin of error of 3% or something. Okay, which means
Go back. You can go.
yeah, which means basically when they conducted a survey, 48% said I support this candidate, but then they're saying, okay, well we're not entirely sure, so we're going to go plus or minus 3%. So the true value could be anywhere between 51 and 45%. Technically, it could even be outside of that, but it's most likely the plausible range is between 45.
But it would be 0.22 middle of that thing, right?
Yes, so in this one it would be 0.22. Yeah, cool. And there, yeah.
So just to go over it again, so basically we took the sample proportion, and from the sample proportion we can kind of make a guess of what the population proportion would be.
Yes, and that's exactly what we're doing, okay? So because this goes in the middle, I'm going to go a certain amount above and a certain amount below, okay? And I'm going to go the same amount above and the same amount below, okay? So I'm going to write something called plus or minus, okay? So I go above or below, so plus or minus, and the quantity over here is known as the margin of error. Okay, and this margin of error we find by doing z times the standard error. Okay. And now actually I'm going to put a star next to z. Z star times the standard error. This is known as the margin of error. It's just symbols, okay? It's
Why
not.
did you put a star?
I'll explain. Okay. To specify that it's a particular value of z. Okay, so z star times the standard error. Okay. The standard error. So let's talk about the standard error. SE is standard error. The standard error is pretty much the same thing as the standard deviation of the sampling distribution. Do you guys remember what that was?
Oh, right.
Yeah.
You did it above.
It's the square
square
root
root, yeah.
of p times 1 minus p divided by n. The key difference here is that we aren't using p, we're using p hat. Why are we using p hat and not p? Because we don't know p. Well, the whole reason why we're doing this is because we're trying to estimate what p is, right? I don't know what proportion of Los Angeles is Asian, okay? I don't know that. I'm trying to estimate it. So the best guess I have right now for p is the current estimate that I have right now, which is 22%, my sample, which comes from my sample.
So okay, so that's not the equation for standard error.
This is the standard error. This is the
but
standard
it
error.
looks just like,
With a p hat.
It's got
difference.
hats now.
There.
but the other one we could also use p hat.
The other one you couldn't.
Oh, I
The
thought
other
you
one
said
was just P.
or
That's only for this checking conditions,
Oh,
large
okay.
sample. That's the only. I know. There's all these. There's P's and there's P hats and probabilities, and it's like, oh gosh. Okay. I know it sucks. All right. I don't know how to make this any more fun.
The margin of error is
Z star times the standard error, okay? What is Z star? Z star is known as our critical value. It's just a dramatic name for a number.
Those two formulas are the same, right? Those two. That one and that one.
What two?
The first one and the second one.
Wait, what's the second one?
This one here. That's one. Isn't that one formula?
This is one formula.
Correct. And then the second one.
This is something else. This is what you plug in to
This
right
is the
here.
standard of error, and that's the margin of error.
Yeah, the standard error is this, and you plug that in right here. And then you multiply
Right,
the
got it.
standard error times Z, and that gives you the margin.
Got
of
it.
error.
Got it.
Okay. Z is the critical value. Okay.
And then error.
You're just gonna have to either memorize these numbers, or more likely, you're just gonna put them down in your note sheet.
Right.
Okay. So put these on your index card. Okay. And these depend on how confident you want to be in your answer. Okay. So for example, okay, let's say we saw that in our sample 22% were Asian. Okay. I could be like, whatever, 80% confident that the true proportion is between 20% and 24%. If I wanted to be more confident about the true proportion, what would I do to my range? I would make it bigger, right? Okay, I could say, oh, now I'm 90% confident that it's between, I observed 22%. I'm going to say I'm 90% that it's between 18% and 26%, okay? If I wanted to be 100% confident, what do I have to say? It's between 0 and 100%, right? Okay? But that 0 and 100% is useless, right? But I could be like 99% that it's between 1% and 40% or something like that, okay? So Z is a critical value, so based on how confident you want to be, you just make your range wider or smaller, okay? And so the numbers that we're going to use, 80% use 1.28 for Z. 90% use 1.645. 95%,
That's like standard, right?
yeah, this will always apply for
Critical. These are critical.
critical values, okay? And if you want to be 99%, use 2.58.
These
okay?
are how close you wanna be, how certain you wanna be?
No, it's kind of, it's just some, quote, magic number that we use to make our range wider to give us more confidence about where the answer is.
So if you use 99%, what does that mean?
It means you're very confident that it's going to be between these two values, but what you've really done is you just made it wider, right? So I mean, just imagine you are the police, okay, and you saw a criminal run into some neighborhood, okay. So this is like in Boston, right? They were on the manhunt for the bomber, right?
Yeah.
And so so what they did was they created a police zone. They created a perimeter, and they said nobody goes in and out, and we're going to search this whole entire area, okay? But the guy wasn't in there, okay? Now, if they wanted to be absolutely sure of catching the guy, all they had to do was they had to make the perimeter a little bit wider, right?
Right.
Okay? So if you want to be more confident about getting the true value of the true proportion somewhere inside this zone you're creating, you just have to make it bigger, okay? But the trade-off is, when you make something bigger, well, in the police case, you've got a larger area to search, okay? Or in our case, we're just we're less. There's we're less specific about something, right? Okay, we're less specific. So.
But
So where do you get these numbers, like 80% use 1.28 meaning?
Where did I get these? Okay.
No, I'm saying like, what do I do? I'm plug it in?
Yeah, we just
Plug
plug
it
them
in
in.
there,
We just
in
plug
the
them
margin
in.
of
Where I
error.
wanna be?
Yeah. Okay. Based on how sure you want to be. Okay.
So you're gonna ask us,
So I'm
I
gonna
want
say.
you to be 80% sure.
I want you to be 80% confident in your answer. Give me some range of where this is going to be.
And then
Okay?
I just plug in the SC.
And then you just plug in all of these numbers.
What
What's the plus and minus greater? Never mind.
What's plus or minus? That's going to tell you the upper end of how high you need to go, and the minus will give you the lower end.
Wouldn't
Okay.
wouldn't a person want to have a larger area to get the proportion, just in case they miss out? So
Yeah.
that's-
But right? Why didn't the police just block off all of
Yeah,
Boston and search the
because
entire
it's
city?
inconvenient
Well, it's just
for the rest of the people that live there.
yeah, it's inconvenient.
For the
okay?
rest of the people that
For
live
the
there.
rest of the people that live there. Okay, now in
But
math, the
practical.
numbers don't have feelings and they're not inconvenienced. Okay, but okay, what's more useful, right? I say, oh, you know what? You're like, okay, so you say, okay, I'm gonna throw a party for people. Okay, you know, how many slices of pizza do you think the average person eats?
Right.
Okay, and I could say, oh, you know, I'm pretty confident that the average person eats between 2 to 3 slices. And then you could say, okay, well, if we're gonna invite 100 people, I should have something between 200 and 300 pieces, or pieces of pizza. Okay, all right, but then, but that's like I'm only 90% confident. Okay, if I want to be 99% confident, I have to say, oh, what's the average number of pieces of pizza someone eats? I'll be like, oh, it's gonna be between 0 and 10, okay? And then you'd be like, okay, well, if I invite 100 people, I gotta make sure I have between 0 pizzas and 1,000 pieces of pizza, okay? That's not as useful, right? Now you have
That's
no idea.
expensive.
Well, that's expensive, but now you really have no idea how many pieces of pizza to order, okay?
But it's rather. But people always say you rather have more than less, so then at least you
Well,
accommodate.
yes, but yeah. So, do you want to order 1,000 slices of pizza? No. Okay, so you got to create a range, and you can say, okay,
Right.
well, I'm pretty confident this is going to be good enough, but you know, there's a chance I'm going to mess up. So you don't want to just pick the widest range
Right.
possible because it's not as much use.
Yeah.
I just wanna write notes again, what's the plus and the minus, so it's
The plus,
P
because
hat
we're
plus
making a
minus.
range, right? We're making a range. So right in the middle, I'm putting whatever I observed. Okay. So I said, you know, what proportion is this? Right in the middle, I observed something. This is my best guess right now, but I don't know if this number that I observed was high or less. So I've got to kind of create an interval. Okay. So let's try the example. Okay. So we surveyed 200 randomly selected people in Los Angeles. Okay. And, So randomly selected is met. Okay. And then we're going to say 44 of the 200 are Asian. Okay, so based on this, make a, we'll say 90% confidence interval abbreviated CI, for the proportion of Asians in LA. Alright, can you guys do this?
Let's try it.
Try it.
It's confidence what?
Confidence
interval.
interval. Confidence interval.
Alright.
I'm sorry, 90% what? And it's
Confidence interval.
Oh.
Confidence interval. Okay, which is alright. Here, I'll just do it, okay? Because we're gonna run out of time. We're gonna run out of
Just
time.
show us the steps.
Okay, so what is my p hat?
44 over 200.
44 divided by 200. So p hat ends up being 0.22. Okay, so again, to find my confidence interval, I put p hat right in the middle, and I go up or down some amount, the margin of error. The margin of error is z star times the standard error. P hat is 0.22. 90% confidence interval, what is my z star that I'm going to use? 1.645. And then my standard error is what? How do I find my standard error? It's going to be the square root of 0.22 times 1 minus 0.22 divided by
Square
200.
root.
Okay, and I square root the whole thing. So if you have a fancy calculator, you can just put this all in one line, and then it's two steps. 0.22 times parentheses 1 minus 0.22 close parentheses divided by 200. You hit equals, and then you do well, depending on your calculator. For me, I do square root answer key equals. Okay, so these are the exact buttons I'm going to put in my calculator. And I get 0.02929. Okay, that's my standard error. I'm going to multiply this times 1.645.
0.
I'm sorry?
He's asking if that's a 0 or 6.
Oh, that's a 0. Sorry. Okay, and so I get this number to be 0.048. .22 plus or minus 0.048. So basically, my estimate, if I'm 90% confident, I estimate that 22% of Los Angeles is Asian with a margin of error of 4.8%. Okay, or 5%.
So it's either plus 0.
Yeah, it's going to be in between there.
Correct.
Okay, so I would say I am 90% confident that the proportion of Asians in LA is between, okay, so I have to do 0.22 minus 0.048, and that gives me 0.172. Okay, so it's between 0.172 and I do 0.22 plus 0.048, 0.268.
Oh, that's right.
Okay, so this is my low end, and this is my high end. Okay, so I'm saying I'm 90% confident that the proportion of Asians in LA is between 17.2% and 26.8%. Okay, 90% confident it's between these two numbers. Is it possible that the proportion of LA that's Asian is some other number outside of this range? Yeah, it's possible, but that just means our random sampling is just kind of was a weird sample. I happened to just get an unusual sample that either gave me too many or too few Asians. Okay?
I have a question.
Yes.
For stuff like this, are you going to be asking us if we can do this is going to include checking the conditions for the sample and
You know, technically we should always be checking conditions, but I'll make sure, for these problems, when the problem is doing this, I'll make sure the conditions are met, okay? If I asked you to make a 95% confidence interval, what would you do differently?
Just change the
I just don't use 1.645, I use 1.96, okay? What would happen to my confidence interval? Does it get bigger or smaller? It gets bigger, okay? I'd be 95% confident it's between 16 point something percent and 27 point something percent. So now I have to just create a wider range, okay? It's just, now you're less precise about your answer. Alright, you're going to see a confidence interval problem on the quiz next week, so study these
Do we have a
examples.
quiz next week?
Yeah.
There is a quiz next week.
On this chapter only?
On just this chapter. Everything we've done on this chapter. It's an
So
important chapter.
everything we did today?
Everything we did today, you'll see on the quiz.
That's cool. I like that.